Okay, so in our GPUs we have these little cores, and inside each core they are very small, simple arithmetic logic units, and they can do operations, floating point operations. Actually, what you do is, for each core, you program what to do. This is how deep learning libraries compatible with GPUs are being constructed. Or you could be a GPU programmer, you could do it yourself, but most GPU-capable libraries like TensorFlow, PyTorch, or MATLAB Deep Learning Toolbox, they have these. What they do is they put little pieces of codes inside these kernels, and they are very simple codes. And they are, in NVIDIA's terminology, called kernels, guys. They are called kernels. So in NVIDIA's GPU language called CUDA-C, you can write kernels to each guy. And a kernel in a GPU device actually looks something like this. For example, it's a block. It's matrix multiplication block. What it does is, it makes a matrix multiplication and it's add over it. It's a matrix multiplication. You're multiplying two matrices and getting a value. So it is, these are the dimensions. As you can see, these k's are the same and you're getting this. It's a matrix multiplication. It only does this, for example, this kernel does it, using the memory available in this cage. Wonderful. It is doing it very fast. And actually in this paper, let me show you that paper again. It is a very nice paper. What they do is they are implementing the GPU kernels used for deep learning to FPGA-based systems and comparing the speed of them. Where I'm going to discuss this when we come to FPGAs as well. And this paper has very nice background information on what kernels are, what kind of different kernels you can have, how different kernels have different speeds. So what is this simple atomic operations, scientific operations you can do on GPUs? If you want to get more information, I strongly recommend you read this paper. And especially if you're doing a embedded systems, if you're planning to do an embedded systems master's thesis, this is one of the very nice papers, guys. Okay, let me continue. So this is how you program. Inside each core, you write something like this. So let's talk about another dimension aspect of the GPUs. So what do we have is, we have the peripheral and flexibility issues of the GPUs. Peripherals, it's talking to the outside world. When we were talking about CPUs, we said that CPUs are very good at it. They're very flexible. You can just talk to any device. Well, this is not the case for the GPUs. GPUs were initially designed to be coprocessors, which in time became processing units of their own. So they are coprocessors to CPUs. Well, I have never seen an application in which GPUs are not being used with CPUs. So you have a CPU which is running everything. GPU is doing the heart of it, doing the hardcore computation of it. That's why, regarding peripherals, GPUs are very limited because they don't have to. Some guy is putting the necessary information to their caches specifically so that they do these simple operations. Somebody has to manage it. That somebody is flexible and is good with peripherals. So in order to communicate, they use their own limited GPU cache memory. So for applications just like ours, deep learning applications, convolutional neural networks, video processing, and image analysis, signal processing, or graphical applications, which doesn't need intermediate access to random data in your memory, well, it's their perfect choice. That's why they are being used for these scientific applications, not running operating systems. How about their programming? I mean, they are not easy to program just like CPUs, but GPU coding has become very widespread, and GPU coding can be considered coder-friendly because you're writing codes like these to the systems. Well, you have to have an idea about the underlying architecture, and you write your codes according to this architecture. For example, you put a part of the image to this memory and the filter. This is running a part of the image here, and this is running another part of the image here. So you have to know how the image is is kept in this part of the cache so that you could put each of the indexes here properly. So you need an underlying, you need to know the underlying architecture. That's good, okay. But still, you're writing codes like this because this is simple code. When you just check it, if you spend 5 seconds on the code, you will easily understand that this is a simple matrix multiplication code. So it's not as easygoing as CPUs, but they are still easygoing because compared to, for example, the FPGAs, they are not. Their GPUs are more friendly. Okay, what about their, embedded architecture? How they are we know GPUs as PCI cards. Most of you play games in your computer, and if you have a desktop computer, inside your desktop, in the PCI bus, which we call this PCI bus, it's a big card like the half of my arm. It's a long, big card, but imagine I'm going to put it on a flying UAV. It has to be small. There are very recent embedded solutions, guys. NVIDIA, the main company that produces GPUs, they've created this Jetson series. They are simpler and more limited in accuracy. In computational power and computational power, but they are more power efficient and they're very small. So you can find different embedded solutions for them. So they are becoming more flexible every day, and we can say that. Okay, I think maybe we should finally talk about the disadvantages of using GPUs for deep learning. Well, the biggest drawback is the memory access. The memory access in a GPU has to be limited and confined. For CNN, this is not a big problem. But for more complex deep architectures, which are not simple serial networks, this can become a problem. Imagine a directed acyclic graph deep neural network where everything is connected to everything like our brain. In that case, those little kernels will have to access many different places. In that case, it will be a bit more difficult to implement the deep neural architecture to a GPU. But regarding the simple architectures like the UNets or AlexNet or the encoder networks, they are a perfect match for GPUs. That's why they have been used widely in the last 10 years. And another big weakness for GPUs is their very well-known, their notorious high power consumption. Well, if you create little arithmetic logic units instead of a single big one, your power efficiency architecturally falls. You spend a lot of power. That's why GPUs are very power hungry, guys. They require additional complexity around their computational resources to facilitate, so that you can write individual codes to each core. This creates lower power efficiency. GPUs are the worst in terms of power efficiency for embedded systems regarding deep learning. That's their biggest drawback, maybe. Okay, I think that's enough for GPUs.